All right, it's 9:40, so let's get started. Um, so I'm going to be going over the concepts in magnetism and some of the uh, information that we went over in terms of electronic structure in this review. So this is going to be taking from uh, primarily material that you saw on exam one. That's I think is pretty important, and you'll probably encounter on the final. So with that in mind, let's just get into it. Um, sorry, there we go. Um, so in our to start our discussion on magnetism off, it's important to establish the differences between non-magnetic materials and magnetic ones. So we usually refer to non-magnetic materials as diamagnets, meaning that they are weakly repelled by applied external magnetic fields. So most things fall into this class of materials in that most things usually don't have unpaired electrons in their valence shell, meaning they're a closed shell, and as a result, their only interaction with an applied magnetic field comes in the form of small eddy currents that are generated, which produce fields in opposition to the applied field. So this gives rise to a small negative magnetic susceptibility and a repulsive interaction between your chunk of material and the field. So illustrated here in the picture is an example of what's called the Meissner effect, where we have instead of an ordinary chunk of material which has finite resistance, we have a chunk of superconducting material which has zero resistance to electric current. And as a result of this, when we apply a magnetic field, the repulsion or the expulsion of that magnetic field from the interior of the material is complete, and we get this nice magnetic levitation effect, which is quite useful. So conversely, paramagnets do have unpaired electrons in their structure, and as a result, they have a comparatively large and positive magnetic susceptibility due to the spin angular momentum of the electrons. However, just because something is paramagnetic doesn't necessarily mean that there's any form of magnetic order in the material. In fact, most paramagnets do not have any magnetic order. Excuse me. So in order to actually get our spins to line up with the, in order to get our spins to line up in any meaningful way, we have to actually apply a magnetic field, because otherwise, without the magnetic field, our spins can just be randomly oriented like so within our sample. There's no real reason for them to be lined up in parallel. So the oft-cited example of paramagnetism is molecular oxygen, so O2. As I'm sure you should all be aware by now, in the MO diagram for O2, you end up with two unpaired electrons, so an S equals 1 ground state. And because of this, if you cool the oxygen down enough, number one, and you apply a strong enough magnetic field, the oxygen will appear to be attracted to the magnetic field. And that's illustrated here in the picture, where we have a little puddle of liquid oxygen suspended between the two poles of a powerful magnet. So the interaction that gives rise to a paramagnet's attraction to a magnetic field is what's known as the Zeeman interaction. So under zero field conditions for paramagnets, there's no preferred orientation for the magnetic moments. And as a result of that, the different M sub S states, which correspond to the different orientations of the spin in space, are all degenerate, meaning they're all the same energy. So, however, when we apply a magnetic field, these states split up in energy, giving rise to a preferred orientation. So that's illustrated in this diagram here, where we're plotting energy in wave numbers as a function of field for an S=1 ground state. So for oxygen, for instance. So as you can see, as we apply a field, the m sub s equals +1 state, which is the state where our spin is lining up in parallel with the field, gets lower in energy. Our m sub s equals 0 state, where our spin is orthogonal to the applied magnetic field, it doesn't change at all. And our m sub s equals -1 state, which is anti-parallel with the field, gets higher in energy. And you'll note that the scale we're talking about here is quite small. These values are on the order of 5 to 10 wave numbers generally, even for really large fields. And as a result of this, to really observe this magnetic ordering, quote unquote, as that arises as a result of the Zeeman interaction, you have to usually cool your sample down quite a bit in order to depopulate these excited states. Hence why you don't see oxygen concentrating itself around magnets as a gas. You have to cool it down so that it enters the liquid state. So with that said, we can move on to a discussion of the different types of magnetic order that we saw in class. The first and most simple type is that of ferromagnetism, where we have all of our spins in our material lined up in parallel with one another. This occurs as a result of a positive exchange interaction between spins and their neighbors. So as a result of that, the spins tend to line up in parallel with one another. And we don't actually have to apply a magnetic field to get this to happen. So this occurs spontaneously. However, we do have to be below what's called the Curie temperature, or the ordering temperature of the material, in order to observe this. Whereas if we're above the ordering temperature, the spins will be randomly oriented though they were in a just simple paramagnetic material. So shown below are some examples of this in, I guess, reality, nature, where metallic iron displays this behavior. Obviously, ferromagnetism refers to iron. Metallic gadolinium also displays this kind of behavior below at lower temperatures. And of course, the neodymium iron boride magnets are also ferromagnetically ordered. So the second type of magnetic order that we saw is called antiferromagnetism, where instead of having a positive exchange interaction, we have now a negative exchange interaction between the neighboring spin centers. And as a result of this, we get this anti-parallel arrangement of our spins. This is quite common. And two examples of this in nature are manganese oxide, where we have S=5 manganese centers coupled antiferromagnetically, and metallic chromium. So while these materials are magnetic and have unpaired electrons in them and are magnetically ordered, they don't, because of the fact that we're lining up our spins in an anti-parallel arrangement, we get no net magnetic field out of these materials. So unlike ferromagnets, where we can polarize them pretty easily, these are not natively polarized below their ordering temperature. I should also note that the ordering temperature for antiferromagnets is not called the Curie temperature. It's referred to as the Néel temperature. And so the final form of magnetic ordering that we saw in class is what's called ferrimagnetism, where we still have a negative antiferromagnetic exchange interaction, but instead of having identical spin centered or identical neighboring spin centers, we now have non-equivalent spin centers. So This is also quite common in materials where we have multiple metals in multiple oxidation states. So magnetite, where we have iron 3 and iron 2, and I cannot pronounce this word, pyrrhotite, I think that's how it's pronounced, where we also have iron 2 and iron 3 in some fraction. And as a result of this, the fact that our spins are not fully compensated, we do get net magnetic moment, even though we have a formally anti-ferromagnetic exchange interaction. And again, these also have ordering temperatures associated with them, and they also need to be cooled below their ordering temperature in order to actually display this magnetic ordering. So with that, let's get into the different mechanisms for exchange that we saw in class. So the first and probably the most frequently encountered exchange mechanism is that of superexchange, where we have two neighboring metal ions or spins bridged by a diamagnetic atom or anion. So shown here is just that for manganese oxide, where you can envision we have two possible spin configurations where either the manganese atoms have their spins lined up in parallel with one another or anti-parallel with one another. And you can envision that in the parallel arrangement, we can delocalize one of the oxygen electrons over one of the manganese centers, but not the other one, due to the Pauli exclusion principle. However, when we have an anti-parallel arrangement, we can delocalize both, and as a result, this is a lower energy configuration because because this lowers the overall kinetic energy of the system. And because of this, superexchange generally results in an antiferromagnetic interaction. The second type of exchange, or a different type of exchange that we discussed in class, is called double exchange. And this is superficially similar to superexchange. However, excuse me. In this case, we have two non-equivalent metal centers. And this is common in valence delocalized materials. So you can envision a scenario where we have a metal denoted here as M1 and an oxidized form of that metal, which I've noted as M1+. And we can have a core of unpaired electrons, or of a single unpaired electron, and a higher orbital through which we're transferring an electron. So you can envision two scenarios here where we can have all of our electrons in parallel with one another and one in an anti-parallel arrangement of our electrons. So on the left here, if we were to transfer this higher energy electron to the vacant orbital on the right, Hund's rules would remain satisfied and the kinetic energy would be low. However, in the event that we have an anti-parallel arrangement, as shown on the right here, transferring this electron would lead to a violation of Hund's rules, which gives us a higher energy state when we do the electron transfer, and as a result, our kinetic energy is raised. And so for Hund's rules to hold, we need a ferromagnetic arrangement of these spins, which means that double exchange generally gives us a ferromagnetic exchange interaction. There are other exchange mechanisms that we went over, namely direct exchange, where we don't proceed through a bridge and don't necessarily have to have different oxidation states. And again, and to make it clear, you can have multiple different exchange mechanisms operative at the same time. So generally speaking, the mechanisms that you'll have to be familiar with are superexchange, direct exchange, and double exchange. I don't have a slide on direct exchange though. So, Okay, so for to kind of take our discussion on exchange further, um, the uh, the geometry of the, I guess, the metal ligand metal interaction also matters. So to kind of illustrate this, with super exchange and manganese oxide again, if you were to have a 180-degree metal oxygen metal angle, this maximizes the orbital overlap between the diamagnetic p orbitals on the oxygen and the magnetic d orbitals on the manganese atoms. And as a result of this, we get a maximal antiferromagnetic superexchange interaction. However, if we have a 90-degree angle, these orbitals are now orthogonal. And as a result of this, Coulombic exchange dominates, meaning that we want to satisfy Hund's rules in order to achieve the lowest energy, which gives rise to a ferromagnetic, or what appears to be a ferromagnetic exchange interaction. It's worth noting that because we lack the orbital overlap here that we have in the antiferromagnetic case, that this ferromagnetic interaction is going to be a lot weaker than the antiferromagnetic interaction. And to kind of fully tie this together, when we look at the actual neutron diffraction pattern, or neutron diffraction structure of manganese oxide, we can see that the exchange interactions differ as we as we look at different planes of the material. So in the 111 plane, which is denoted by the dotted lines shown here, we can see that the spins are lined up ferromagnetically with respect to one another, which is a result of this 90-degree orientation of these ions with respect to oxygen. Whereas if we're in the 001 plane, which is here, it's worth noting that this plane contains the oxygen atoms in the structure. The exchange interaction is largely antiferromagnetic, as denoted as JAFM. It's also worth being clear that, or it's also worth noting that these exchange interactions are not exclusive to solid state materials or extended solids. These are also present in molecules, in a large number of molecules, I should say. So this is one that you've seen before, manganese 12 acetate, where we have 12 manganese atoms in different oxidation states. So a total of 8 of them are manganese 3, and 4 of them are manganese 4. And the manganese 3 plus ions are S equals 2, whereas the manganese 4 ions are S equals 3 halves. And the S equals 2 manganese ions couple antiferromagnetically with the S equals 3 halves manganese 4 plus ions. And this gives rise to an overall ground state of S equals 10. Yes. So moving on, so what we were discussing previously is mostly atomic scale structure and physics associated with magnetism, whereas now we're going to be discussing effects that occur on the order of hundreds of thousands to millions of atoms. So the length scales we're talking about when we talk about magnetic domains are much, much longer. What magnetic domains are essentially are regions of our material that are polarized in a certain direction. However, we can have different regions of different polarization in the same ferromagnetic chunk of material. So this, to have essentially random orientations of polarization in our material actually lowers what's called the magnetostatic energy, as well as increases the entropy of the material, which is energetically favorable to have occur. So this is, and we can get rid of this disorder by applying a strong magnetic field to line up all of the domains in the same direction. So that's illustrated here where at zero field, we have all of our domains canceling each other out. However, within the domain, itself, these spins are ferromagnetically coupled. However, as we apply a field, we can favor the growth of one domain over the others. And as we continue to increase the strength of the field, we can fully unify all of the domains into a single domain, I guess. So it's worth noting that below the ordering temperature, the spins within domains are ordered. However, the domains don't necessarily need to be ordered themselves. So to kind of illustrate why the what gives rise to this lower energy configuration, we can go from A to C here and show how the subdivision of this domain lowers the external magnetic field and therefore lowers the energy of the system. So in the case of A, we have a single domain where we have maximal external magnetic field. But when we divide this domain into two domains of opposite polarity, we can lower that magnetic field, however, not quench it completely. But when we subdivide further, we completely quench the external magnetic field of the material. And this in and of itself lowers the energy. However, the increase in entropy associated with doing this also is a favorable process. So this domain growth and migration is what gives rise to magnetic hysteresis and bulk magnetism. So to kind of walk you through this plot again, on the y-axis we're plotting sample magnetization, which is the the strength of the magnetic field coming off of our sample, versus an applied magnetic field, which is H. So at the start, we're at zero field, our sample is fully demagnetized. But when we apply a strong enough magnetic field, we can fully saturate the material, as shown here. And then when we sweep backwards, usually we will lose some amount of our magnetization, but we won't lose all of it because there's below the, but we won't lose all of it because the domains can't actually migrate to fully reform this zero magnetization configuration shown here. And in order to do this, we actually have to apply a field in the opposite direction to get those domains back into the zero field configuration. And this field value that we need to apply is what's known as the coercive field, whereas the magnetization that remains on the sample at zero field is what's known as the remnant magnetization. And we can cycle from here indefinitely. Okay, so with that, I will switch gears and I'm going to start talking about some of the electronic structure concepts that we went over that will be important in understanding single molecule magnetism as well as magnetism in general. So I talked a little bit about Hund's rules already, but we should go over what these actually are because they're pretty important. You all kind of intuitively know these from freshman chemistry, but the way that they're taught is not always totally clear. So just to make it as clear as possible, there are three such rules for determining the ground state electronic configuration of an atom. So our first rule is we want to maximize our term multiplicity. And what this means is we want to, our ground state electron configuration is going to have the maximal total spin quantum number that it can have. So remember, the total spin quantum number is just the sum of the individual spin contributions from all of the electrons in our atom. So we want to maximize this value. The second rule is to maximize L, which is the orbital angular momentum of our ground state. And just recall that L is, the largest L value is going to be the largest possible big M sub L value, which is the sum of the individual small m sub L components from all of the different electrons. And the last rule is a conditional rule, but if our valence shell is less than halfway full, we want to minimize our total angular momentum quantum number, J. If it is more than halfway full, we want to maximize this value. And it's important to remember that the result of this process, of this treatment, is an electron configuration that gives us the lowest possible electron-electron repulsion and the lowest possible electron kinetic energy in our atom. Furthermore, it's also important to remember that these rules only really apply when we're in the LS coupling scheme or the Russell-Saunders coupling scheme. If our spin-orbit coupling is sufficiently strong, as it is in really heavy elements, we need to use a JJ coupling scheme in which we can no longer individually sum the spin and orbital contributions of the electrons. We have to sum small j values essentially to get our j values, our big J values rather. Okay. So to kind of illustrate Hund's rules, we can take terbium 3+ as an example. The first thing you do when you're trying to determine the electronic ground state of an ion is you need to count the valence electrons of that ion. So for terbium, we just start here and count backwards. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And since we're trivalent, we need to subtract 3 from that number. So 11 minus 3 is 8. So we have a Xeon core and a 4f8 electron configuration for terbium 3+. So in finding the ground state, we need to apply rule number 1, which is maximize S. So to do this, it's pretty simple. You just fill in the electrons unpaired first, and then start pairing them up as after you fill up halfway. So when we do that, we get an S value of 6 halves, which is equal to 3. In applying the second rule, we want to maximize L. And again, you can do this by finding the maximum EMPS of L value that you can get for this particular electron configuration. And that's shown here, where we have this electron paired up in the EMPS of L +3 orbital, which is fx times x squared minus 3y squared. So what that gives us is a maximum L value of +3, +3, +2, +1, +0, -1, -2, -3, +3, which is just 3, right? And in applying the last rule, we want to find the maximum J value, right? Because again, we have this orbital set is more than halfway filled, right? So to maximize J, we add L to S, and to minimize J, we subtract L from S and take the absolute value of that. So we just add L to S, and that gives us a value of 6. So that's all illustrated here. And our ground state term symbol for this is 2s plus 1, which is the multiplicity, F to represent an L value of 3, and 6 to represent our J state of 6. Okay. So it's also worth noting that the symmetry of free ion term symbols is analogous to that of orbital symmetry. So to kind of illustrate this, I have shown on the left here what should be pretty familiar to you by now, which is how the d orbitals transform in octahedral symmetry. And on the right, I have how a d term transforms in octahedral symmetry. So for d orbitals, we get a small EG set of orbitals and a small T2G set of orbitals. Whereas for a d term, we get a big EG term and a small T2 or a big T2G term when we descend to octahedral symmetry from spherical. And this is true for all of the terms. So an s term will have analogous symmetry to an s orbital. A p term will have analogous symmetry to a p orbital. D term to d orbital. F term to f orbital. G term to g orbital, if you want to go that far. So all of that is analogous. It's worth noting that you can't determine what the energies of these, that the energy splitting of these is not necessarily analogous, but the symmetry is analogous. So if you're asked to determine the irreducible representations of a term simply, you shouldn't be confused. You should be able to determine those. Okay. So why did we? So we learned about term symbols so that we could determine the state parentage of our different crystal field split states in transition metal compounds. So, and to do this, we need to look at what's called correlation diagrams and apply the non-crossing rule. So shown here are our free ion terms and their associated irreducible representations on the left. And when we apply crystal field, these terms are ordered in this manner as shown here. And to apply the non-crossing rule means essentially terms of identical multiplicity and symmetry cannot cross one another. So focusing on this triplet T1G set here of triplet F parentage and the triplet T1G of triplet P parentage, if we cannot draw a correlation between this and the triplet T1G in the ground state, or this and the triplet T1G in the excited state, because this would result in a crossing of these two states with identical symmetry. When this happens, these states mix and essentially they mix and we get this state up here anyways, and we get this state down here anyways, even if we want to correlate this to the excited state and this to the ground state. So you don't need to know how to order these, but given the order on the right, or the order on the left and the order on the right, you should be able to draw a reasonable correlation diagram using the non-crossing rule. I'm not going to go into this because I think Maria is going to talk about this in more detail. Okay, so that brings us to single molecule magnetism. So single molecule magnetism differs from bulk magnetism in that we're concerned about what gives rise to the permanent magnetism of single molecule magnets is what's known as zero field splitting. So if you'll remember back to the Zeeman splitting diagram that I showed earlier, the m sub s states of that s equals 1 ground state were degenerate under zero field, meaning that there's no preferred orientation of the paramagnet under zero field. However, in single molecule magnets, this isn't the case. We have something what's known as zero field splitting, where the m sub s or m sub j states are split such that we get a preferred orientation even under zero field. So one can imagine this inverted parabola as being the ideal zero field splitting pattern, I guess you could say, for a single molecule magnet, in that if we were to polarize our magnet in this minus 10 m sub s state, and then depolarize it, that is, take it back to zero field with all of our population in this at minus 10 state, in order to get to the other side and relax or depolarize the magnet, we would have to traverse this barrier, which is composed of the different m sub s states. And to do this, we would have to absorb some thermal energy. And so if our molecule is cold enough, it won't have enough thermal energy and it won't be able to relax, and therefore it should display some permanent magnetism. It's worth noting that, so in discussing zero field splitting, the transition metals and lanthanides, the source of zero field splitting in these is quite different. So for transition metals, as you know, the crystal field splitting is on the order of tens of thousands of wave numbers because the d orbitals, whether they be 3D, 4D, or 5D, are all quite diffuse and all can interact strongly with surrounding ligands. Furthermore, because of this and combined with the Jahn-Teller effect, which serves to lift orbital degeneracies in transition metal compounds, our orbital moment is often going to be 0 in our ground state for transition metal compounds. This means, coupled with the fact that for many first-order transition metals, our spin-orbit coupling magnitude is quite low, means that our electronic ground state is determined foremost by our crystal field interaction, and the spin-orbit coupling is what determines our zero field splitting. For the lanthanides, it's a different story because our 4f orbitals are so radially compact and core-like. The crystal field interaction is actually what gives rise to the crystal field splitting, whereas the spin-orbit coupling is what determines the electronic ground state. And what these different lines correspond to are the different J states that we can assume. That is the different J values of the electronic term symbols that we can have. So for a single molecule magnet, we want to maximize this zero field splitting magnitude and maximize the amount of moment that we have in our ground state. So we want to have large J values and large numbers of unpaired electrons, as well as a large zero field splitting. So for transition, a good example of a transition metal single molecule magnet is this linear cobalt compound that was shown in class, where we have this cobalt-2 D7 species ligated by 2 alkyl substituents in a linear fashion. And this complex is unusual in that our crystal field splitting is quite small, and it's special in that the crystal field splitting is small pretty much. And we have a linear geometry. And this gives rise to a non-alpha ground state where, unlike in most transition metal compounds where we have a nominally L equals 0 ground state, this compound has a nominally L equals 3 ground state, which you can kind of tell based on this diagram where we have M sub L is +2, -2, +1, -1, and 0. So if we sum up those contributions, our maximum L value under Hund's rules here will be 3. And because we have non-zero orbital moment here, the zero field splitting as a result of that spin-orbit coupling is much larger than it is for most other transition metal compounds. And as a result, single molecule magnet behavior is also quite large, or is also significant. So an example of a lanthanide single molecule magnet is this trivalent or dysprosocinium compound, where we have trivalent dysprosium and 1- cyclopentadiene triterbutyl ligands shown here. And while the 4f orbitals are really compact and aren't really affected by the presence of ligands, the M sub J states of the lanthanides, which are the coupled total moment states of the lanthanides, have different electron distributions associated with them, and so they split due to the presence of the crystal field. And as a result of the shape of this dysprosocinium compound and the strength of its ligand field, we can get a pretty large barrier to relaxation, as shown here, on the order of 1400 wave numbers. And this barrier to relaxation is what gives it its good single molecule magnet properties. So I think I'm just about out of time now. I think I have a couple more minutes left, but that's all right. So I think these are some useful references. in your study of magnetism and F element chemistry. So on top here is something that I think I've already provided you earlier in the class, which is Spalding's Magnetic Materials Fundamentals and Applications. In part one, it has a really good overview of what we covered in class, as well as some more attention paid to the fundamental physics behind what we covered, which I don't think was covered in a lot of depth here, just kind of due to time constraints. So if you're struggling with magnetism, I would suggest reading through part one at least. It should give you a better idea of what's going on. And the second reference is Cotton's lanthanide and actinide chemistry, which is a less brief description of F element chemistry, but it's a more complete description as well. And it does a pretty good job of describing F element basic electronic structure and such. All right, so with that, I'll be happy to take any questions about the slides if you have them. Or if there are no questions, I'll let Maria take the floor.
For the example you did for terbium-3+.
Yeah.
Like, we used LS coupling in that example. Do we need to know when to distinguish between LS and JJ?
Yeah, so LS is good for the lanthanides. However, I think by the time you reach the actinides, it stops being good. I don't think Jeff expects you to know how to use JJ coupling. I think he just expects you to acknowledge that it exists. Yeah, you don't usually need to invoke JJ coupling, although there are some cases that you do need to use it. I can give, or if you're interested in those, I can give you some references on where you would use the JJ coupling scheme.
Cool, thanks.
Yeah. All right. If there are no other questions, I will hand it over to Maria. All I have to do is just stop sharing screen, right?
Yes.
Okay. Stop.
Actually, it looks like I can just take it from you.
All right, there we go.
Where is can you all see my full screen right now?
Yeah, you're good.
Okay, great. Cool, so I'm going to go over some other stuff, nothing to do with magnets, so particularly MO theory, absorption spectra, and reactivity that we covered in class. And yeah, all of this stuff is like taken from the lecture notes or the textbook, so should be able to just go through Jeff's stuff if you want any clarifications on things that I've said today. Cool. So this whole semester we've been, focusing a lot on determining the oxidation state for different complexes. So to do this, just to review, you need to determine the total charge associated with any anionic ligands and subtract that number from the overall charge of the complex to obtain the oxidation state. For determining the DN count of the metal, you subtract the oxidation state from the group number of the metal in question. And to determine the total number of valence electrons, you just add the DN count and add 2 electrons for each ligand. And if you're dealing with a chelating ligand, you get 2 electrons per point of attachment. So some examples here are this tantalum methyl complex has an oxidation state of +5 because each of the methyls has a -1 charge on it. So that leaves us with a total DN count of 0, and the total number of valence electrons is 10 because you have 5 electrons from the tantalum and then 5 electrons from the methyl ligands. Or you can count it instead, where each methyl group has 2 electrons and the tantalum has 0 electrons. Each way you'll get to an oxidation state, or a total valence electron count of 10. For this iron complex, where you have 4 water ligands and 2 chloride ligands, the chloride ligands provide you with a total -2 charge, and since there's a plus charge on the whole complex, that indicates that iron has an oxidation state of 3 in this complex. So iron with a +3 oxidation state has a DN count of 5, and you'll get total valence electron count of 16. So you have 5 from iron, 2 from each of the water ligands, and then 2 electrons from the chloride ligands. Lastly, we have manganese carbonyl cyclopentadienyl complex. And so here we have an oxidation state of 1 because the cyclopentadienyl anion, it has a -1 charge. So your DN count is 6, and you have a total valence electron count of 18. So you have 2 electrons coming from each of the carbonyl ligands, 5 electrons coming from cyclopentadiene, and then 7 electrons coming from manganese. So just a quick recap on crystal field theory. In this model, the ligands surrounding the transition metal ion are approximated as point charges, or negative point charges, and the electrostatic repulsion between the d electrons and of the transition metal and the negative point charges causes it to be destabilized. So the relative energies of the 5 d orbitals depends on how close that they come to the ligand point charges. So going through an example, here we can look at this linear iron complex, which we can approximate with this drawing. So here we have our 5 d orbitals. And so based on this ligand geometry, we know that the ligands, or the d orbital that's going to interact most strongly with the ligands is going to be the dz squared. So since that's an antibonding orbital, it's going to be the most destabilized, and so it'll be highest in energy. So that's then the next highest in energy orbitals are going to be those that have a z component, so the xz and the yz, since they have some interaction with the ligands that are going along the z-axis. And lastly, the xy and the x squared minus y squared will be the lowest in energy because they're in the equatorial plane of the molecule, so they're not going to have any interactions with the ligand whatsoever. So using the same principles for approximating the degree of the ligand interactions with the d orbitals, you can derive all of the following d orbital splittings for various geometries. So you should try this on your own. It's good practice for trying to rationalize the different the relative energies of the d orbitals for different geometries. So next, let's discuss how to construct a molecular orbital diagram. So like we discussed previously, first you want to determine the N count for the metal, what the total electron count is for the complex, the coordination geometry, and the point group of this complex. You also want to decide if the ligands are sigma donors, pi donors, or pi acceptors. Next, using a character table that is appropriate for the molecule's point group, you want to determine the irreducible representation that the metal s, p, and d orbitals belong to. Next, you derive the ligand group orbitals and determine the irreducible representations that the LGOs belong to. Fourth, you plot the relative energies of the metal d orbitals on the left side of your diagram, and then the ligand group orbitals on the right side of the diagram, and then label these with appropriate symmetry labels. Then add in the appropriate number of electrons for the metal and the ligand fragments. Yeah, and just remembering to label the energy at the left side of the diagram. So always label the arrow with energy. Next, you want to decide what orbitals have the correct symmetry to mix. So your symmetry labels can help you with this. Then you want to plot the molecular orbitals, starting with the non-bonding interactions. So these are orbitals that don't have the correct symmetry to mix with any of the other orbitals. And then next, plot the bonding and anti-bonding interactions. Still keeping in mind to maintain the correct symmetry labels. And lastly, you want to add the electrons to your MO diagram, which it corresponds to the total valence electron count. Sometimes you will need to draw cartoons of the orbitals and label the HOMO and LUMO in your diagram. Some helpful hints for dealing with MO diagrams are you should always generate the same number of molecular orbitals as the number of metal and ligand orbitals that you started with. So if you are missing any MO or any MOs, yeah, that's a good sign that, or if you don't have the same amount of MOs as your ligand and metal orbitals, that's a problem. It's a sign that you're missing something. So symmetry labels also provide some information on the degeneracy of the orbitals. So A and B labels will correspond to one non-degenerate orbital, sort of like an s orbital. The E labels correspond to a set of two degenerate orbitals, so like the degenerate EG set in OH geometry or octahedral. And then T labels correspond to three degenerate orbitals, such as the metal p orbitals in octahedral geometry. Figuring out where to plot the metal and the ligand orbitals can sometimes be tricky. So some tips for figuring this out are using the principal quantum numbers as a guide. For the metal, the 3d orbitals are always going to be lower in energy than the 4s and the 4p. And the ligand orbitals generally have a principal quantum number of 2, so those are going to be lower in energy than the metal d orbitals. And so taking a look at the center of your MO diagram, it should look familiar. It should look just like the crystal field splitting diagram that we've been constructing. And the DN count should equal the number of electrons in this part of the diagram. So relating crystal field theory to MO theory, crystal field theory is just a snapshot of a small part of the MO diagram. And MO theory helps us to get a much better idea of what's going on. So lastly, if you have 3 orbitals with matching symmetry labels, mixing creates bonding, one bonding molecular orbital, one roughly non-bonding MO, and then one anti-bonding MO. So an example that I think we went over in the first problem set was like the pi or p orbital molecular orbitals, or the molecular orbitals derived from the p orbitals in ozone. So if you go back to look at problem set 1, that's a good example. So keeping in mind all of these steps that we discussed, let's look at an example. So we're here, our example complex is iron hexachloride, 4-. So the 4- charge on the overall complex suggests that the oxidation state is 2+. And so that leaves us with a DN count of 6 for iron 2. The geometry and point group is going to be octahedral since we have homogeneously ligated iron here. So you're going to have a total valence electron count of 18 since we have 2 electrons for each chloride and then 6 electrons coming from iron. So what irreducible representations do each of the metal orbitals belong to? We can use the character table for this. The T2G representation is going to correspond to the dxz, dyz, and the dxy, which you can see in this quadratic column of the table. And then the orbitals that have EG symmetry are the dz squared and the dx squared minus y squared, which you can again see in the quadratic column. The s orbitals are going to have A1G symmetry since they stay the same no matter what sort of transformation that you apply to them, whether it be like inversion or a C2 rotation. So they have A1G symmetry. And lastly, the p orbitals are T1U, which you can see in like the linear rotations column. So it's X, Y, and Z referring to each of the p orbitals in each of the directions of the Cartesian coordinate. And you can know this because when it's, since the p orbitals are asymmetric to inversion, you can see that they flip sign when you undergo either a C2 rotation or inversion. And so that's also another clue that the p orbitals are T1U symmetry. So chloride is a pi donor. And so the ligand group orbitals are as follows. So the 6 sigma interactions are A1G, EG, and T1U, and then there are 12 pi interactions as well. This is what all of the pi interactions look like, plus just the 2 others in the other planes. But keep in mind that only the 3 T2G and the 3 T1U orbitals interact with the metal orbitals. So they're the only ones that have the proper symmetry to interact with the metal orbitals. So now let's go through steps 4 through 8 for this complex. So the orbitals that we have available to us are these following metal orbitals and these ligand group orbitals. So here is our MO diagram, and this is a MO diagram that will generally apply to all of all pi donor systems. So because we have a pi donor ligand set, the pi orbitals are going to be lower in energy than the metal orbitals, as you can see on the right. So it's important to notice that the T2G bonding set has contributions from both the metal d orbitals and the ligand pi orbitals. And you should also notice how the T2G set has moved up in energy to become slightly anti-bonding due to this interaction with the pi donor ligands. So that is decreasing our delta octahedral. Next we'll go through an example that is a pi acceptor. So in this case, we have 6 cyanide ligands that have negative charge on it. So that leads us to a DN count of 3. We're still in the octahedral point group when we have a total valence electron count of 15. Here we have the same metal orbitals and the same irreducible representation, since we still are in the same symmetry. And we have the same ligand group orbitals, except for we're dealing with a pi acceptor interaction instead of a pi donor. So here we again have the same orbitals that we've seen previously. So now, because we have a pi acceptor, the pi star orbitals are what are going to be interacting with the metal d orbitals, and these are going to be higher in energy than the metal orbitals since they're pi star, so anti-bonding, and they're empty, which allows the metals to donate into them. So now the T2G set has contributions from both the metal d orbitals and the ligand pi star orbitals. Most importantly, because of the interaction with the pi star orbitals of the ligands, the T2G set has moved down in energy, so now they're primarily bonding interaction, and this causes an increase in delta octahedral for the complex. So lastly, we'll look at an example with a slightly different geometry. And this is also a chelating ligand. So the DN count on this complex is D8, since we have palladium 2+. The geometry of this complex is approximately square planar, so it has D4H symmetry. And our total valence electron count is 16, since we have 8 electrons coming from the ligands and 8 electrons coming from palladium. So again, you can use the character table to determine which metal orbitals belong to which irreducible representations. So again, using these rightmost columns to guide you, you can see that the dz squared now has A1G symmetry. The dx squared minus y squared is going to be B1G. dxy is B2G, and then EG is the dxz and the dyz. So ethylene diamine, as you should know by now, is a sigma donor ligand. So there are only sigma interactions that we have to pay attention to with this ligand set. So here are all of the orbitals that we have at our disposal. Notice that there are 3 sets of A1G MOs. So there's bonding, non-bonding, and anti-bonding. 4-coordinate 16 electron complexes tend to be square planar, since this electron count avoids placing electrons in the high energy B1G orbital. So switching gears a bit, we're going to talk about absorption spectra now. When interpreting your absorption spectra, it's important to keep in mind the selection rules that we've discussed. So when you have wave functions that have different spins, the wave functions are orthogonal. So this means this leads to the spin selection rule, which dictates that allowed transitions have a delta S of 0. So a transition with delta S of 0 is spin allowed, while if delta S does not equal 0, it's spin forbidden and should have 0 intensity. So the second selection rule arises because the electric dipole vector associated with an electronic transition is an odd function. You have, by symmetry, the Laporte selection rule. So for centrosymmetric molecules, such as an octahedral molecule, G to G and U to U transitions are forbidden. So since the d orbitals are even functions and the p orbitals are odd functions for an octahedral complex, dp and pd transitions are Laporte allowed, while d to d transitions and p to p transitions are Laporte forbidden and should have 0 intensity. And so that applies specifically to octahedral complexes, but if you have a different geometry, some of these transitions can become available. Additionally, while you're interpreting your spectra, it's important to keep in mind vibronic coupling. So this is just the concept that certain vibrational modes of octahedral complexes will break the inversion symmetry, which briefly allows the transition to occur. And so this is a phenomenon that leads to D to D transitions for, or spin allowed D to D transitions in octahedral metal complexes, leading, so this allows for absorption bands to be visible and leads to the colors of transition metal complexes. So when you're interpreting your electronic spectra, you can use these approximate intensities for determining what type of transition you're seeing. So if you have both a spin forbidden and Laporte forbidden, you're going to have a very low intensity transition. As you are not, or as you start to remove these selection rules from your transitions will grow in intensity. And then, so finally, like the spin allowed and Laporte allowed, as well as charge transfer bands, will have the highest intensity. So I wanted to go over a bit of the information that you can glean from Tanabe-Sugano diagrams. If you want more details about the Tanabe-Sugano diagrams, you can look at the review session from February 21st. I go into a lot of details about like the Rockoff parameter, et cetera, and how to derive your delta octahedral value from this diagram. In this diagram, you have on your y-axis the free ion terms that you can derive as Alex mentioned in his presentation. So here at the origin, you have your ground state free ion term. And then as you increase in energy, you have your excited state free ion terms. And the units for this, or what's being plotted, is the energy scaled by the Rockoff parameter. And so on the x-axis, you have your octahedral ligand field splitting, which is scaled by the Rockoff parameter as well. So you can use the energy as on the x-axis as a proxy for the delta octahedral value. So with increasing delta, it is an increasing delta octahedral splitting. So that should follow that for complexes that have electron counts where you can have a high spin and low spin configuration, the lower the x-axis value, the lower the delta splitting, and therefore you'll have the more likely that the complex is going to be high spin. So in these diagrams, the sides that correspond to high spin and low spin are split with this vertical line that goes occurs at about 20 delta over B. And so when you're trying to determine what transitions are occurring in your spectrum, you have to try and determine what type of ligand you have, and if you expect that that ligand will produce a high spin or low spin complex. So just a few examples. We can use the selection rules to decide which of each of the following pairs of transitions will have a more intense absorption band in the UV visible spectrum. So when you're deciding between the 4S to 4P transition or 4S to 4D transition, the 4S to 4P absorption will be more intense based on the Laporte selection rule, since p orbitals have U symmetry and the D and S orbitals are G symmetry. So which one will be more intense, a D to D transition or a charge transfer band in this nickel complex? So obviously the charge transfer band will be more intense because D to D transitions are Laporte forbidden, as we've discussed. Lastly, which will be more intense, a D to D transition in this nickel iodine complex or a D to D transition in this nickel ammonia complex. So you have to keep in mind the geometries of these two complexes. So this nickel iodine complex is tetrahedral, and so a D to D transition is allowed for this complex since there's no inversion symmetry in for that geometry, and so all the D to D transitions are Laporte allowed. Lastly, I wanted to talk about ligand substitution reactions. So we've discussed that there are two main types of ligand substitution reactions that occur for transition metal complexes, dissociative and associative. So for dissociative, you have your starting complex, which then the transition state loses one of the ligands. So if you are starting with octahedral, you'll end up with a square pyramidal transition state. And then for associative, you gain a ligand as you move into the transition state. So for an octahedral starting complex, you'll end up with a pentagonal bipyramidal or capped octahedron as your transition state, and then you lose a ligand to reform an octahedral complex. And in general, if the energy of your intermediate is much higher than that of the reactant complex, then the reaction will be slow because there's not a large driving force to form that intermediate for the and proceed with the reaction. So I wanted to review some general trends in lability, which can inform how these reactions will proceed. So first row transition metal ions are labile except for chromium 3+ and cobalt 3+. The inert octahedral complexes are those with high ligand field stabilization energies. So in effect, a large delta octahedral splitting. The ligand field stabilization energy is dependent on a number of factors, including the number of d electrons you have, the type of ligand, and the spin pairing energy for the complex. So effectively, if you can evaluate delta octahedral for a complex, you can know the ligand field stabilization energy. Second, high spin complexes are more labeled than low spin complexes. Since high spin complexes typically have more populated antibonding orbitals than low spin complexes, this weakens the bonds between the metal and the ligand, making them easier to break. Second and third row transition metal ions are generally inert unless they're D0 or D10. And this occurs because the second and third row transition metals have larger delta octahedral splittings, which leads to stronger bonding caused by the increased diffusivity of these d orbitals in these larger metal ions. Lastly, for D0 and D10 ions at a constant charge, the lability increases with radius of the metal. So this is caused by shielding of the nuclear charge, which leads to weaker bonding in these metals since they have no ligand field stabilization energy. Oh, fun, my transitions are still there. Yeah, so just a bit about dissociative mechanisms. Here are the elementary reactions. So you have an equilibrium between losing and regaining the departing ligand, and then you have your 5-coordinate transition state for an octahedral complex that then binds to an entering ligand. Mechanisms for ligand substitutions of octahedral first row transition metal complexes are most often dissociative or dissociative interchange. And in order to determine if a mechanism is dissociative, you have to observe saturation kinetics. So this means that high concentrations of the entering ligand, the reaction rate only depends on the concentration of your starting complex, and it doesn't change with the identity of the entering ligand. Additionally, at constant concentration of the entering ligand, the rate depends highly on the nature of the departing ligand, and this can be observed through a linear free energy relationship, where you can correlate the strength of the metal ligand bond to the rate of dissociation of the complex. And so structurally, the point where the entering and departing ligands are equidistant determines whether or not it's a dissociative interchange or just dissociative. So if you have a larger or a smaller metal ligand distance, or the metal ligand distance is smaller at the so if the point at which the entering and departing ligands are equidistant, if that's smaller, then it's a dissociative interchange, and if this is larger, it's purely dissociative. Here we have elementary reactions for an associative mechanism, and this relies on the association of an entering ligand to your starting complex and then the loss of the departing ligand. This type of mechanism is most common for ligand substitutions of square planar transition metal complexes, and the rate of these reactions are strongly dependent on the nature of the entering ligand. And so that's a way to test whether or not you have an associative mechanism is by flooding the starting material with an entering ligand. And you should see a dependence on the type of, the reaction rate should be dependent on the type of ligand that you're flooding it with. And so conversely to the dissociative mechanisms, smaller metal ligand distance at the point which they're equidistant will indicate you have an associative mechanism, whereas a larger metal ligand distance will indicate associative interchange. So I guess it's 11, and that's all I've got for you. So if anyone has any questions, please speak up. Otherwise, we'll let you go.
Will these slides be made available on B-Courses?
Yeah, for sure. We'll post them on B-Courses.
Thank you.
Anything else? Oh, something in the chat. I can see. Oh, okay. Well, if no one has any other questions, I guess we'll post these slides on B-Courses, and everyone have a good weekend.